This is the first lecture for the fourth project, just to talk about system calls. Basically, because we need to have some way of allowing user processes, user applications to start interacting with the kernel. And Project 4 is the first opportunity to do that. So in Project 4, you'll see that there are user tests, and the tests interact with the kernel from user mode. So it actually is pretty accurate representation of what an operating system has to do. So typically we have a trap. There's newer ways of doing that now with sysenter and syscall, but Pinto doesn't use those, so we rely on interrupts. So int80 hex is or int128 is Linux. Then we have 2e for Windows, and Pinto's uses 30 hex. That just happens to be the interrupt that Pinto's traps. So pretty straightforward, not difficult. And the only problem, though, is that getting arguments to the system call handlers, that is challenging because remember that when we switch operating modes, we switch stacks. When you switch stacks, it's harder to pass arguments on the stack. Now, it's funny because I say this, most real operating systems pass all their arguments in registers. For whatever reason, Pintos decided to pass arguments on the stack. So I'll have a couple slides at the end that show you basically a picture of how Pintos works and how to deal with that. But most OSs don't do it the way that Pintos does it. So that'll be kind of an interesting little wrinkle that you have to deal with. Okay, so typically, like I say, they're passed in registers. Now remember, we're talking 32-bit, so even if you took CS24 last year, and saw 64-bit stuff, we're talking about the E registers, not the R registers. So the arguments will be passed in registers. The first register will always be what operation am I performing. So that'll typically be in EAX, or on 64-bit, that's in RAX. And these will be platform specific. And so on Unix systems, there will be a specific file that lists the system call numbers. And it does vary from OS to OS. So like OS 10 does, or I really should say OS X. They used to say OS 10. But OS X will have one set of system call numbers. Linux will have a different set of system call numbers. BSD will have yet another set of system call numbers. So they definitely vary across platforms. Okay? Now the big issue, which is not a real issue, but it is an important constraint to stay within, is that the arguments to system calls have to stay within a register. Now normally this is not a problem because, well, I can always put a pointer into a register. And so if I need to pass information, I can always have a struct that I point to from a register. Or if I need to have a large blob of data, like a buffer or something like that, I can always pass a pointer to that buffer in a register. So really, this constraint is not too constraining, and that's pretty nice. Okay. Rarely, you'll see large arguments split across multiple registers. One thing that you see a lot in Windows System Call API does a lot of passing things in structs. So I'm just going to have a pointer to a struct. In fact, they do this thing where on Windows, I don't know. Have any of you done any Windows programming, like system level programming? Probably not. Okay. So basically, what happens is you pass a pointer to a struct. The first member of the struct is the size of the struct, and that basically allows Microsoft to version these structures. So if they decide, well, we want to add like 4 new fields later on, well, then the second version of the struct will just have a larger size, and the API will know if they see the size argument, the size field of the struct saying it's this size versus that size, they know what the caller is expecting, what they're expecting to be provided. So kind of a neat approach. Works really well. And like I said, it's ubiquitous in the Windows APIs, but it's not very common in the Unix APIs. Okay, most of the time you don't actually interact with these syscalls. Like, you're not dropping int80s in your code or sysenters into your code. It'd be kind of silly to, especially when most of the time the process for getting into the kernel is the same all the time. So typically you'll have wrappers that are provided. So that's what I talk about here. There'll be a standard library. And there's two kind of flavors that you'll see. Okay, that this library stands between applications and the OS. Basically, one flavor is that you'll either have a system or a function call, a standard library call that is just a wrapper. It's basically passing straight through to the kernel. So read, write, close is another great example. Open for files, and then socket for other things. So basically, these things are direct wrappers. All the function does is it plops in the system call number, puts the arguments in the appropriate registers, hits the interrupt, or it calls syscall and gets directly into the kernel. So this is one flavor of library function that you'll see. The other one is functions that are built around kernel interactions, but they don't really, they aren't a direct exposure of it because they may have a more indirect interaction. So malloc is a great example because it manages the heap, and it may ask the kernel to expand the heap for a particular process, but it doesn't do that if it doesn't have to. Okay, so malloc might call set our limit, or it might call sbreak depending on the OS implementation of heap memory for a process. But it's not going to do that every time, and it definitely isn't a direct interaction like read would be. Okay, so that's the idea there. I do want to talk about how this works because I'm going to show you how Linux implements this mechanism. You may want to base certain parts of your Pintos implementation on the Linux implementation. Unfortunately, like I said at the beginning, Pintos deviates rather wildly from most other OSs in that it actually passes syscall arguments on the stack, which is gross and grungy, and you'll see that pretty much immediately. I think that the method behind its madness is that it wants to force you to think about user space memory interactions from the kernel. And so that's why it actually forces that requirement. But it's not very standard. Okay, so how are interrupts and traps handled? I think this was probably a lecture where I was gone. But basically, the user process has a stack. The kernel has a stack as well because it's in a different protection ring. And so you have whatever's on the stack currently, and then it executes a trap. And so we switch stacks. And there's certain things that the CPU does automatically. So it goes ahead and stores the stack pointer to the user space stack. Okay? And when we're switching protection levels, that includes the segment as well as the pointer. So that's going to be, I think, 8 bytes of stuff in a 32-bit architecture. It's going to be more if you're on a 64-bit architecture. Then, again, this is all the CPU doing this. It'll save E flags so that it can clear the interrupt flag, and it'll store the instruction pointer to what was interrupted. And that's, again, in a different code segment because it's switching from user mode to kernel mode. Okay, so now we have this. And the OS is not going to take any chances. So most OSs, what they do is they set up their interrupt dispatch table so that every single interrupt that that could ever occur gets it into a specific handler, so that a random handler going off doesn't cause the kernel to crash. So it'll have a stub for every interrupt, and basically all the handlers do the same thing. Some of the handlers will push a dummy error code because there are a few handlers, specifically the page fault handler. The page fault handler will push an error code saying what happened, what caused the fault. Okay, and so since some of the handlers will push this error code, the other handlers push a dummy error code just to make sure that everything sees the stack looking exactly the same. Okay, and why would I want to make the stack look exactly the same? Well, it's so that I can make a struct, and then I can cast the stack pointer to the struct pointer, and then I can just access all the members of the struct easily and have names, and everything is just a lot cleaner. So now I can start doing stuff from C, okay, or some other language that you might prefer. Like C++, you could certainly do this in C++ or Rust easily. Okay, so error code, and then the interrupt number is pushed. So every stub is going to say this is the interrupt number for the stub, and that'll be pushed onto the stack. And then basically the context of the interrupted kernel thread or interrupted process will be pushed onto the stack as well. Now, since we're talking traps, it'll be the interrupted process, so that'll all be pushed onto the kernel stack as well. Okay? So this is basically exactly what the stack is going to look like. Okay, and now the interrupt service routine can do whatever it wants, and so it can change registers, it can maybe re-enable interrupts if we support preemption, it can switch to a different kernel thread because, hey, we have all the state of the current kernel thread saved. Okay, so yeah, interrupt service routine gets the program CPU and register state. So like I was saying, all we really need to do is cast ESP to a struct of the appropriate type, or a pointer to a struct of the appropriate type, and then all of this junk becomes accessible. And that's what's so cool about this mechanism, is that it's really easy to access and manipulate the machine context and work with those values. Okay. Now the other part of this is that the system call handler will return some results. So when you call read, you get an error code back that says if you succeeded or not. You call close, it'll return an error code depending on what happened. And so basically, the way that this gets passed back is you'll notice that the system call handler returns a status result in EAX. This is just part of the calling convention. Okay? That, just like in 64-bit, the result is returned in RAX, and 32-bit, the result is returned in EAX. And so basically all we have to do is go manipulate the register state of the interrupted program. We just write the value on the stack, plop it into where EAX is restored from, and now the caller will see the return value of EAX that we want it to. Okay? So that's pretty neat. It's a pretty straightforward mechanism for doing so. Okay? But ideally, this is the thing that I think is really neat about last project, which is going to be coming to an end on Friday, and also the next project, is that it sort of really makes this whole notion of machine context transparent. And so to me, it'll help cement an understanding of the process abstraction. So that's a really nice characteristic of this pair of assignments. Whereas initially, the whole idea of threads and thread context switches and scheduling can be a little bit confusing. This is going to make it really transparent. Okay, idea of the system call. Typically what happens is, we might have 100 or maybe even more system calls that we need to support. How do we actually support all these things? Well, the easy way of doing it, if you remember from CS24 how a switch statement works, how the compiler will translate a switch statement into a table of pointers of snippets of code that handle each option. Well, we can do the same thing with an array of function pointers that are pointers to the various service routines, one for each system call. Okay, so we can do this dispatching mechanism, and basically the way that most OSs do this is they'll have a sys underscore version of every entry point into the kernel. So you have write, then you'll have syswrite. You have read, you'll have sysread. You have fork, you'll have sysfork, and so forth. Okay? And basically, these things end up in an array, and then the system call number specifies the position in the array. So syswrite, there would be a pointer to syswrite at the appropriate index that corresponds to the system call number for syswrite. Okay? Now, I'll talk about that in a second. So basically, the service routine, again, so you're talking int 80, you're talking int 30 for Pintos. The entry comes in, and it sees, okay, this is system call number 17, so it goes, looks at index 17, and dispatches to the function that is specified for that entry. Okay? So pretty straightforward. Now, on the aside here is actually kind of interesting, which is that sometimes if you're implementing more complex operations, you need to read stuff from files. You need to write to files. You may need to fork a process or whatever. And so the sys underscore versions can be called within the kernel, because there's no point in trapping into the kernel again to do some operation. So instead what you do is you just call a service routine implementation. So exposing these as functions makes it really helpful. If you need to build a complicated operation from these simpler operations, you just call the routine. Okay? So that's the idea there. Are there any questions so far? It's all really straightforward, right? I mean, it's just, this is a good way of engineering a system to do this kind of thing. Okay, now, of course, when that system call number comes in, let me just back up and say the rule of thumb is never trust anything from the user process. Okay? So anytime anything comes from the user process, you verify it. You always have to verify. System call number is the first obvious one. Typically, the system call numbers are in a range, and so if something is beyond the max, then you immediately know this is not valid, and so you can just return this error code eNoSys. Now, if I remember correctly, a lot of times these things are actually inverted. I don't remember if it's true for Pintos or not, but you'll see that the system call routines specify that the error code will be negative. And so it might be minus eNoSys rather than just eNoSys. But that's the idea. Okay? So you check to see if the ID is in range, and that's no problem. Oh, and of course, if you have something in the middle, so it's below the max, but it's still a system call number that doesn't correspond to a real system call, well, you just have a helper routine whose whole job is to just return eNoSys. Okay? And then you can just register that for any part, any system call number that doesn't correspond to a real call. Okay? So that's easy enough. This is how Linux does it. So here is a little bit of the Linux system call handler. And again, this is going to be the int80 hex handler. So this is the thing that handles invocations. So we've already gone through the CPU saving of the minimal state, and then the, what should I call it? The interrupt handler has gone ahead and saved the machine context so that we can now do whatever we want. And now we're inside the system call service routine. Like this is the thing that does int30 or int80 or whatever. So first thing we do, compare EAX, remember that's the system call number, to the actual number of system calls we have. If it's less than that, we're good. We come down here. Otherwise, yeah, so this is what I was talking about. We just returned minus eNoSys. Notice this weird thing though, we're saving this constant into 24 ESP, which is a little bit confusing. You see magic numbers more in assembly code than you do in C code or C++ code. But all we're really doing here is writing this value to where EAX will be restored from. So that when we leave system call and go back to the user process, they'll see EAX set to minus eNoSys. And so they'll say, oh, okay, somebody passed an invalid system call. Okay, so the kernel's still bulletproof. That's nice. Now the next thing that we do is we have this table which has an entry, a pointer, a function pointer to each system call service routine. Okay? And so we just take the value in EAX, multiply it by 4, because pointers in 32-bit are 4 bytes, and we look that up, look up that entry, and we just invoke it. Okay? We invoke it indirectly. Recalling, of course, that if it's an invalid system call number, there will be a routine there that just says eNoSys, so that we don't have to worry about that. Okay, so we invoke it, it returns, and then we take whatever EAX was, move it to where it will be restored from when we get back to user process, and then we're done. Okay? So it's pretty straightforward. I mean, the Linux system call implementation is nice and clean, and it's modular, so that it's easy to go in and manage these service routines very straightforwardly. Okay, does that make sense, everybody? It's pretty nice. Okay, now here's one fun wrinkle, and you will run into this with Pintos as well, that different system calls require different numbers of arguments. Some may require none. Some may require 1. mmap is crazy and requires a lot of arguments. But remember, read requires 3 arguments, write requires 3 arguments, close requires 1 argument. So we have different system calls with different numbers of arguments. And the question is, how do we use that with this generic mechanism? Okay? So we have the fact that these arguments come from the client, let's say the user process, in specific registers. And these service routines are actually written in C. They expect their arguments to actually appear on the stack. And again, this is a deviation just for people who took CS24 last term. Normally, C routines in 64-bit expect the first 6 arguments to be passed in registers. So this is a little bit of a difference. But in 32-bit, you expect all your arguments to be passed on the stack. There were fewer registers available. There's only 8 instead of 16. But anyway, it would look something like this. Notice EBX is the first argument, ECX is the second, EDX, ESI, EDI, EBP. And notice how cleanly they're laid out on the stack. ARG1 is the lowest value, ARG2 has the next higher address, and so forth, all the way up. Okay? And so the system call handler actually pushes these registers onto the stack in reverse order. Okay? So that the argument 6 has a higher address than argument 5, which is higher than argument 4, all the way down. Okay? So you get this layout. Now it turns out that this actually follows exactly the CDECL calling convention. And CDECL is what the compiler uses on 32-bit. I should say Unix platforms on 32-bit use this calling convention. And the neat thing about this is if you have a function that only takes 2 arguments, well, the assembly code that's generated from the C only accesses the first 2 spaces. It doesn't care that there's other things. If you need all 6, well, then the code generated accesses all 6. If you take no arguments, you don't access anything on the stack. You just do your thing. So this is really nice because basically it allows the system call service routines to access the arguments that they need. System call, the thing that dispatches, always pushes everything that could be accessed onto the stack. Okay? The fact that arg6 is pushed is immaterial to something that takes only 2 arguments, so it just pushes it anyway and then dispatches. Okay? So it's a nice, clean, generalized way for this to work. So here's the simple example. Notice syswrite takes 3 arguments, so EBX, ECX, EDX will be the first 3 arguments. The file descriptor, the buffer, and the size. And so syswrite will access those things just using its, it'll actually in the C code say FD and buff and size and all of those things without any problem. And the code generated by the compiler just will work properly with this because the system called dispatcher makes sure the stack is set up properly. Yes?
Is this like an extra line you added, or lines you added to sysnode, like that notepad sys?
What do you mean? Can you elaborate?
To push these values onto the kernel stack.
Yeah.
Where does that happen?
That would have happened in the code snippet that I showed you,
Yeah, the assembly.
but afterward, yeah, in the part that actually invokes the service routine.
Yeah, right before the call.
That's right. Yeah, it would take care of that. Yeah, it's hard. This is actually, I mentioned the textbooks that would be helpful for the class, and what is it? Understanding the Linux kernel. I think that's it's either Understanding or Insight. I can't remember which, but it's a guy holding some Fresnel lens or something, and yeah, that one goes through the code, and it's hard to cram it all onto a slide. But yeah, that's basically where that would occur. Okay, so then system call dispatches to syswrite. Syswrite sees the arguments that it wants. It sets up the stack frame in the way that CDECL specifies. And again, what I would say is that you probably will want to review CDECL. You'll want to review the CDECL calling convention for the user process system call project, just to make sure you're familiar with how the stack is laid out. Because, like I said, since we're switching CS24 to 64-bit, there's now sort of an impedance mismatch between 24 and 124. At whatever point we actually roll out a new OS, instructional OS, it'll be 64-bit, and then there won't be a mismatch. But we'll have this mismatch for probably a few years while we figure this out. Okay, so any other questions about this mechanism? This is just an illustration. It's a good illustration, and I certainly encourage you to try to achieve the same level of modularity in your implementation for Project 4. We always seem to find that the people who try to do this have the cleanest and best results. Okay, so something to consider. You can do it more ad hoc if you'd like. You may lose some points for style, but whatever. Okay, so like I said, we don't trust anything from user process. We already checked the system call number. That was one thing we obviously had to check. But we need to check everything else. Okay, and the big general issue that we have is that we like the kernel can do anything. The kernel can access any facilities on the hardware. It can access anything in the memory mapping. So if we're in user mode, like the user process can't do very much. If it tries to touch kernel space, it gets a fault. And a well-written kernel will just kill that process. So if we're in kernel mode, we can do anything. And so if we're taking pointers from user processes and just trusting them, we're basically being idiots. And so we need to be really careful about this kind of thing. So here's read, just to give you a simple example. Okay. File descriptor, buffer, and bytes. So what this system call does is it reads some number of bytes from the file and stores them at the pointer passed in. Okay. What is this pointer? Well, we don't want to presume that the pointer from the user process makes sense or is nice, and that a user process isn't trying to do something naughty. Okay, so this is what I said. So yeah, the pointers are expected to be user space pointers, but what if the user mode process decided to specify an address that was in kernel space as opposed to in user space? Okay. Again, the process can't touch that pointer, but it certainly can pass in a value and cast it to a void star, and the compiler will accept it. So you can imagine that if a kernel naively trusted that pointer, it would just write to whatever the thing was that it tried to specify. Okay. Yeah, so as long as the user mode program doesn't dereference that pointer, we're fine. Okay. So this could be really problematic, and it could be problematic in a couple of ways. I mentioned targeting critical data structures. Let's say you have a file, and you put data in it that you want to inject into the kernel. Maybe it's code, maybe it's data that you want to overwrite critical data structures or something like that. Then you call read, you say, hey, read this file and stuff it where I tell you to. And the kernel naively does it, and now you're sad. Okay. So another possible issue is that the user process tries to crash the kernel just by specifying some pointer that it doesn't know if there's actually a memory mapping or not. One of the things you'll notice is that in 32-bit, we have a whole gig allocated to the kernel space. Most kernels aren't going to use that entire gig. So you have pointers that may be meaningless to the kernel. In 64-bit, it's even larger. You have, I think, current typical 64-bit x86 systems will divide the address space in half. So half of it is user space, half of it is kernel space. Again, large numbers of addresses that don't correspond to anything. Okay. So basically, we need to make sure that any address the kernel dereferences has to actually come from user space. The kernel has to verify this stuff. Okay? If it's not in user space, we automatically flag it as a problem. We don't even dereference it, we just flag it as a problem. Okay? Here is the layout of a Linux process in 32-bit, so that's why we have 4 gigs of space, and like I said, the kernel user boundary is at 3 gigs. So the upper gig is the kernel, and this is clearly not to scale. But then we have various other things that are, user space layout is rather complex. So how would we verify that addresses are okay? Well, there's a really easy way. We just make sure that it's below that boundary. Okay? So we say, is the address less than C0000000? That is defined as a constant in Pintos. I can't remember the name of the constant, but it's like fizzbase or something like that, or maybe it's not fizzbase. But there's some value that is defined in some file that says this is the boundary between user space and kernel space. Okay, so that check all by itself will keep the kernel a lot safer. Okay. Yes.
You also need to check that certain places in the user space that the thing should write to either don't get right, like the program text or the forbidden zone.
You could, but yeah, I'll talk about that a little bit. This is the right slide to talk about that issue on, because you have various things that can occur. I mean, I have listed here. You have a pointer to memory region that isn't allocated yet, so it doesn't appear in the page table, or it's an access that would be invalid. Okay? So you have to figure out how to handle these kinds of things. The way that most OSs handle this is that they will just perform the access and then let the page fault handler deal with the crap. Okay? So you try to access something that's not allocated. Well, at this point in the system call handler, we don't know if it's not allocated because the page just hasn't been given to the process yet, or if it's because that address range is not valid. The system call handler doesn't know. Same thing with a write. How do I know that I'm performing a write to a region that's invalid to perform a write to? Or perhaps I'm doing copy on write, or perhaps the page is, it's a perfectly valid place to write to, but the page isn't loaded. We need to swap it in. So you can imagine all these circumstances that could occur. And so, again, you want to achieve a separation of concern. So the syscall handler handles the system call stuff, and the page fault handler would resolve all that stuff. Now, in you guys' implementation, I'll just tell you how a lot of people do it on Project 4, is there's basically two ways in the assignment given of how to handle this stuff. You can either, you're the kernel, you have access to all the data. So you can go look up in the page table of the user process and see if it's a valid address. And a lot of people choose to do it that way for Project 4. It's a pretty nice way of doing it. But it is a little slower than letting the hardware do that stuff directly. And so the other approach that's available for Project 4 is to use the page fault handler to tell you when an access is invalid. I kind of leave it up to you guys. The assignment suggests that the page fault approach is more typical, and I think in a fully fledged operating system it is, but you may want to choose the simpler look up against your page table approach for Project 4 and then deal with virtual memory in Project 5. Like, don't deal with page faults quite yet. There's something nice about having page faults being relegated to kernel bugs. It's kind of a nice warm blanket that if I see a page fault, it's because my kernel has a problem. That goes away completely in Project 5 because now you start doing virtual memory. Okay. Does that answer all your questions? Hopefully it answers them and more. That's one of the biggest design questions that you can run into on this upcoming project, and it always makes me nervous. Okay, so the OSD is a page fault or a protection fault inside the kernel. No biggie. But the thing that's challenging is that it isn't always an error, and so that's the big challenge. Like I was saying, we may not have allocated the page yet. We may have copy on write pages. We may have other things. We may have a swapped out page. That's a third option that I don't have listed here. So maybe not allocated, maybe it's swapped out, maybe we have copy on write. Okay? So this complicates the system call handler. Yeah, so this is what I was saying before, that in Project 3, page faults are always bad. Project 4, page faults may be bad, depending on how you approach it. And Projects 5 and 6, well actually, you can do 5 and 6 independent of each other. You actually get extra credit if you build the file system on top of virtual memory. But if you don't want to deal with that, which I wouldn't blame you, then you can build the file system separate from virtual memory. And so Project 5, page faults start meaning other things, and so that's the challenge of dealing with that. Okay, so here's the deal. OS sees faults within the kernel. That is, kernel code does something and causes a fault. And sometimes that's valid. Sometimes it's a user program misbehaving, passing an invalid pointer. And sometimes you have kernel bugs. Right, you guys, some of you have seen this. I do an operation in my kernel, and I get a page fault because the kernel's doing something wrong. Okay? So here's the interesting question. How do we figure out which of these circumstances it is? Okay? We're going to assume that I can identify the valid scenarios or user process passing an invalid pointer. But the question is, how can I tell when I have a kernel bug or an invalid pointer? Okay? So that's the question. So how do we distinguish between faults caused by addresses, passed to system calls, and ones caused by bugs. Now, the reason why I'm presenting this question is because Linux has a really fascinating solution to this. Fascinating to me. Well, that's why I teach the class, I guess. But one of the things we don't really talk about in this class is the ELF file format. And you all have done this all the time. You've been doing this since the first time you used any compiled language, so probably CS2. But you compile junk and you see those .o files. Those are ELF relocatable object files. And then you link them together and you get an ELF executable binary file. It turns out that you can create a whole bunch of different kinds of ELF formats. And ELF has this really neat thing where you can create sections. Some of the sections are standard, like .data, .bss, .text. But then you can create other sections for other purposes. And so here's the question that the Linux developers ask themselves. Of the whole kernel, remember, we're talking a monolithic, modular, monolithic kernel. Of all of that kernel code, how much of it is actually interacting with user space? Well, if you think about it, I've got system call handler. That's like the only thing that's really interacting with user space, right? Everything else in the kernel is probably just doing kernel stuff. It's handling interrupts. It's interacting with buffers that devices can write to, so that's probably kernel space. So basically the bulk of what the kernel does is going to interact with kernel space. There's just a small amount of it that's done in user space. Okay? So basically what the kernel does, and this is in the system call service routines and so forth, is it'll say, hey, I'm about to touch user space. Hey, I'm done touching user space. And it'll record those address ranges into this thing called an exception table. And the exception table just says, these are the addresses of instructions in the kernel that interact with user space. And so what happens in the fault handler is that the kernel goes and looks in the exception table and it says, does this address that caused the fault, remember the address that caused the fault, there's two addresses involved. Okay? There's the address that was read or written, so we have the memory access, that is an address. But we also have the instruction that caused the fault. And so the page fault handler looks at the instruction that caused the fault and see if it's referenced in the exception table. If it is, it says, well, probably this is a bad pointer from the user process. Okay. If the faulting instruction is not in the exception table, then the assumption is that it's a kernel bug. Okay. The kernel dereferenced null, the kernel accessed something else that's just in la la land, we don't know where, but basically it decided to access something that was invalid. Okay? And so what it does when it has a kernel bug is it actually tries to salvage as much of the situation as it can. It's kind of funny, but if the user process does something to the kernel and manifests a kernel bug, that process dies. And this is basically to try to save the OS. You know, we're going to sacrifice the process to save the OS. And so we basically print out information saying, we just had a kernel oops. Here's some information about what happened, when, where, why. And then the process is terminated, and ideally the OS continues to be stable. Okay? So you can see that a kernel oops is like a mild version of a kernel panic. A kernel panic typically brings down the whole OS. Okay? But if you get a kernel oops, then you say, oh, I hit a bug. Ideally, I didn't corrupt state, so maybe if I just kill the process, we'll be okay. That's the idea. All right, yes?
Could you, for the, having like an exception table where you register like the instruction addresses, could you also just have like a global flag that you kind of like you set before you're about to access user private pointers? And then
It's possible that you could have a per kernel thread flag that had some detail like that. So you set the flag when you're about to touch user space, and then you unset it when you're done. The only challenge there is in the context of preemption is you'd have to be able to coordinate the fault with the kernel thread that did the access. And so that's the only detail there that you'd have to worry about. but it seems feasible. It seems like a feasible approach. So yeah, that might actually work as long as you ironed out all those other wrinkles. Would that be better? I don't know if that'd be better or not. I just don't know. But it's an interesting question. It's an interesting idea. Okay, here's an example of a kernel oops, and this is mainly, I mean, it's like who runs Solaris anymore? Really, nobody. But that's probably not true completely. But still, I wanted to show this to you just because it has a cow. Um, your system had a cow. Anybody familiar with cowsay? Turns out that there's this little utility on Linux. I think you can install it on your Mac. I think I installed it on my Mac for funsies. But basically, you can make a cow say whatever you want. And so that's basically, you can see that historically this goes back quite a ways. And you can even make the cow dead or whatever. You can make the cow asleep. In this case, the cow's dead. But that's an example of a kernel oops, dumping out information, and ideally somebody can figure out how to deal with this. Okay, questions? Right. This is the kind of thing that's happening behind the scenes when your app crashes and then it says, do you want to send a report of this crash to wherever, you know? So sometimes you get useful information, and nowadays people just upload it to the company, and ideally some developer looks at it. Okay, Pinto system calls. For the remaining time, I'm going to give you a little bit of a heads up about the weirdness that is Pintos, so that you can be aware of that. Okay, so it does not follow the standard mechanism precisely because the arguments are passed on the stack, the user stack, not in registers. And I don't know why. It doesn't make sense. I do say that it complicates the system call mechanism, but it turns out that it's not that bad, actually. Except that you just need to be careful that you're accessing, because if you're accessing user stack, you're accessing user space, and you need to make sure that you're accessing valid data. Okay, but this is basically the picture that you need to think about. Okay, and you'll notice that I have references to the files that define these things, so that you can go look it up. Because I don't hate you all, I want you to be able to find this stuff relatively easily. But the kernel thread stack is set up basically the way that we had before. But then you have the system call arguments that are actually stored on the user process stack, and you have to access them from the user process stack. Okay? So interframe. This is basically the machine context that the kernel system call handler gets to see in Pintos. And you'll notice that it's got a whole bunch of junk. Okay, we have EDI, ESI, EBP, blah, 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 all of this stuff. Okay? And then you have all this other stuff. And you'll notice something interesting. Remember that I said that the CPU pushes stuff first. Stack pointer, stack segment, because we're switching from user mode to kernel mode. Then we have E flags, CSIP, so those are the, that's the instruction pointer that was interrupted. So notice the push by CPU, but that's at the bottom. Why is it at the bottom of the struct and not at the top? And then we have the error code and the vector number, and then we have the actual context, machine context of the interrupted process. The thing to notice is that C structure members are assigned increasing addresses. So when I have the struct laid out this way, EDI has the lowest address, ESI has the next higher address, and so forth, all the way down to where ESP and SS have the highest address. What this means is that if I'm considering the stack, remember that the stack pushes the first things at the highest addresses. So this is making, it's in this order so that the CPU push stuff is in the appropriate place, and then the error code and the vector number, and then the machine context is the lowest position on the stack. Okay, so that's the reason why it's backwards, or seems to be backwards. Okay, but what happens is basically you get a pointer to the inner frame, and then you can access anything from the machine context that you want. You can write to anything on the machine context that you want as well, like setting EAX to the return value of your system call handler. So you can just go ahead and modify inner frame and make sure that that value gets stored. Okay? So what I point out here is that you can pull the ESP member from down here where it's saved by the CPU, and that'll point to the bottom of the user stack. Cast that to an appropriate pointer type, like uint32t is a great idea. Remember, this is 32-bit architecture. And then you can just access those elements like an array. Okay. I believe, I can't remember, there may be definitions like pound defines for the various locations on the user stack. But what you can do is define your own constants if there aren't already constants, so that's easy to do. But it follows cdecal, so the first argument will be at the lowest address. Actually, I think the system call number is at the lowest address, and then the next address is argument 1, argument 2, argument 3. You're just increasing values. Okay, so if you cast it to an array, it'll be really easy to access. Okay, does this make sense? One other weird wrinkle is the question of why is there ESP and also ESP dummy? Well, again, if you took CS24 last term, then you didn't get the benefit of this helpful instruction. But in 32-bit, so IA32 has push A, push all registers. For some reason, it pushes the stack pointer, but it's using the stack pointer to know where to push the registers. So it's weird, but the stack pointer is actually saved as part of push A. So that's the ESP dummy. That's the thing pushed by push A. ESP down at the bottom, that's the one that's actually restored when we go back from the interrupt service routine. So the bottom one is the important one. But ESP dummy is just the one saved by the machine context. Okay? I just wanted to point that out. All right, let's see. What else do I talk about here? Yeah, so this is basically system call arguments. If you were to cast it to a 32, I should say an array of 32-bit values. This follows cdecal. So the arguments are pushed in reverse order, and there may be 6, there may be 2, so you can't guarantee that there's going to be as many arguments as you need. You just need to access as many as your system call handler requires, and then the system call number will be the lowest value. So you just you can use a system call number. One of the things that some people do, and I'll just give you this little hint for your implementation, is that they'll make this table, this dispatch table for system calls, and each entry in the table will actually be a struct as opposed to just a function pointer. And the struct might be function pointer, number of arguments this function requires. Okay? And that way you can say this system call function needs 2 arguments. This one needs 3. This one needs 0. And that way it makes it easier for the system call service routine to do the appropriate thing. Okay? I mean, there's a lot of different ways to do this. So if you come up with something that's reasonably clean and straightforward and extensible, then you should do perfectly fine for this part of the assignment. Okay, yeah, then read the arguments themselves. And since you're accessing user space, basically you have, this again is where you have options. What would I recommend for this assignment? I really don't know. I think, honestly, in all of the OS class, I would always pick the simplest thing. This is a hard class as it is, so I would pick the simplest thing. The simplest thing may indeed be looking up against the page table of the process to see if it's a valid address before you try to access it, and then you can just access it directly. You know it won't cause a fault. If you want to be fancy and clever and learn extra junk, you can try doing the page fault approach. But honestly, it gives me a bit of the willies. So, but you'll be dealing with some of that stuff. I don't know. See, that's the thing. The page fault approach may make Project 5 easier, but it may make Project 4 harder. And so that's why I'm just not sure what advice to give you. So, but, the one thing I'll tell you that's really important about Project 4, Project 4 is the one project that actually is needed for the rest of the projects. If you completely jack up Project 3, that's okay. You can actually roll back to the original Pinto's code and build Project 4 without any Project 3 code. But the problem is projects 5 and 6 both build on project 4. So you have to nail project 4. That's really crucial. So that's why I would say you may want to consider taking whatever the simplest approach is for getting this argument checking stuff working. Okay, any questions on that? Yes, question.
Could you just check the user's stack base pointer to see if stuff is valid in the stack?
You could, but I don't know that that's actually going to buy you anything because I'm just worried that one of the tests may modify the stack pointer in some invalid way, so that if you're just looking at the stack pointer, you still get in trouble. So you do actually run into that in Project 5 because you can subtract a big bunch of space from your stack pointer to allocate space on the stack, and then those pages haven't been allocated to the process yet. And so just looking at the stack pointer is helpful in limited ways. You may still want to look at the actual process address space definition. Okay, last thing that I'll tell you. The next 3 lectures, I'm scared to do this, but I want to because I am really excited about these topics. The next 3 lectures are not required because unfortunately Pintos isn't sophisticated enough to get into this. But what we're going to do is talk about signal handling, how signal handling works. To me, it's one of the coolest, more advanced topics that you can get into in kernel implementation. And again, we're at Caltech, so I figure you should understand the hard stuff. So we'll talk 1 lecture about signal handling. It's really cool. And then we'll spend 2 lectures talking about how kernel allocators work. Because remember, they have a very different problem than the general purpose memory allocator that your programs run against. Since the kernel is the longest running piece of code on your system. And so we'll take 2 lectures to talk about that. So I hope you come. If not, I'll be sad, but yeah, it's not required for the assignment. So we'll see you next time.